The art of dynamic programming, mastering optimal substructure and overlapping subproblems in the world of algorithms and computer science. Dynamic programming stands as a powerful technique that transforms complex problems into manageable subproblems. This approach is particularly effective when faced with optimization challenges where solutions can be built incrementally using previously computed results. Dynamic programming shines in scenarios involving overlapping subproblems and optimal substructures. By storing intermediate results through memoization, we avoid redundant computations and achieve significant performance improvements. This article explores how to harness dynamic programming's potential to solve intricate computational puzzles efficiently. Understanding the core principles of dynamic programming at its heart, dynamic programming relies on two fundamental properties: optimal substructure and overlapping subproblems. These characteristics define whether a problem can benefit from a dynamic programming solution. Optimal substructure means an optimal solution to a larger problem contains optimal solutions to its smaller subproblems. Overlapping subproblems occur when different decisions lead to solving the same subproblem repeatedly. Without addressing these overlaps, algorithms may waste resources recalculating identical solutions. Recognizing both features allows developers to determine if dynamic programming is applicable to their particular challenge. To illustrate this concept, consider the classic Fibonacci sequence calculation. A naive recursive approach would recalculate values many times, but with dynamic programming techniques such as memoization or tabulation, each value needs only be computed once. Optimal substructure. Solutions to larger problems depend on optimal solutions to smaller ones. Overlapping subproblems. The same subproblem appears multiple times during computation. Identifying problems suitable for dynamic programming. Before applying dynamic programming, programmers must assess whether a given problem exhibits the necessary traits. Common indicators include situations requiring maximization/minimization operations, counting possibilities under constraints, or finding shortest/longest paths in graphs. Classic examples such as the knapsack problem, longest common subsequence, and matrix chain multiplication demonstrate these patterns clearly. These problems often involve making choices at various steps that influence future decision-making processes. A crucial step involves determining what constitutes a state in the problem space. For instance, in the case of the longest increasing subsequence problem, states could represent sequences ending with specific elements. Additionally, identifying recurrence relations helps express how current states relate to previous calculations. This relationship forms the foundation upon which dynamic programming implementations are built. Fundamentals of memoization techniques. Memoization serves as a key strategy within dynamic programming by caching results of expensive function calls. It prevents redundant computations while maintaining the integrity of recursive approaches. Implementations typically store pre-computed values in lookup tables for quick access. This method works best when combined with recursion, although iterative versions also exist. Memoization requires careful design to ensure that every possible input combination is accounted for without unnecessary memory consumption. An essential aspect of successful memoization lies in choosing appropriate data structures. Hash maps, arrays, and dictionaries offer varying degrees of efficiency depending on the nature of inputs being stored. For example, when computing factorials recursively with memoization, a simple array might suffice since factorial n depends solely on n. However, more complex dependencies require multidimensional storage mechanisms. Tabulation versus memoization. Choosing between iterative approaches while memoization emphasizes top-down recursion with caching. Tabulation follows a bottom-up approach by filling out a table iteratively. Both methods aim to eliminate redundant calculations but differ significantly in implementation style and memory usage. Tabulation generally provides better control over memory allocation compared to memoization, which might suffer from stack overflow issues due to deep recursion depths. Programmers need to weigh trade-offs between ease of implementation versus resource management requirements. Choosing between these strategies depends largely on problem specifics. tabulation excels at handling well-defined ranges where iteration order matters, whereas memoization offers flexibility in exploring diverse branches of computation trees. Consider matrix chain multiplication as an example. Here, constructing a cost table via tabulation ensures that each entry builds upon earlier calculated entries systematically. Design patterns in dynamic programming implementation. Effective dynamic programming solutions often follow recognizable design patterns that simplify development and debugging efforts. One common pattern involves defining base cases up front before proceeding with general case logic. Establishing clear boundaries for initial conditions helps prevent errors related to undefined behavior or incorrect assumptions about edge cases. These foundational elements provide stability throughout the entire algorithm execution flow. Another prevalent pattern focuses on iterating through dimensions according to dependency relationships among variables. Proper ordering guarantees that required information will always be available when needed most. Implementers should also pay attention to space complexity considerations by optimizing memory usage wherever possible without compromising correctness or performance metrics. Case studies, real-world applications of dynamic programming. The power of dynamic programming extends beyond theoretical exercises and finds practical applications across numerous domains including bioinformatics, finance, artificial intelligence, and operations research. In bioinformatics, DNA sequence alignment leverages dynamic programming principles to compare genetic material effectively. Algorithms like Needleman-Wunsch employ scoring matrices to find alignments with highest similarity scores. Financial institutions utilize dynamic programming models for portfolio optimization tasks, risk assessment analyses, and derivative pricing calculations. These applications help manage uncertainties inherent in market dynamics. Operations researchers apply dynamic programming extensively in logistics planning, inventory management systems, and scheduling algorithms aimed at maximizing productivity gains. Evaluating time and space complexity trade-offs when implementing any dynamic programming solution. Understanding time complexity becomes paramount. Generally speaking, reducing the number of operations translates directly into improved runtime efficiency. Spatial complexity concerns arise primarily from the size of auxiliary data structures used during computation phases. Balancing these factors requires thoughtful consideration based on specific application requirements. For instance, some problems allow trading off extra memory against faster lookups by pre-computing additional layers of information up front rather than calculating them dynamically during processing stages. Careful profiling techniques enable developers to pinpoint bottlenecks and identify opportunities for refinement that yield substantial benefits without excessive overhead costs associated with redesigning core architectures. Advanced optimization strategies in dynamic programming. As practitioners become proficient in basic dynamic programming techniques, they naturally seek ways to refine their implementations further through advanced optimizations. One promising avenue involves leveraging sparse representations for certain types of problems. Sparse data structures minimize memory footprints by only allocating storage for non-zero elements or other meaningful values relevant to particular contexts. Such optimizations prove especially beneficial when dealing with high-dimensional spaces characterized by vast empty regions. Parallelism represents another exciting frontier in modern DP research areas. By distributing workloads across multiple processors or cores simultaneously, substantial speed-up advantages emerge for large-scale instances featuring extensive interdependencies. However, parallel implementations demand rigorous synchronization protocols ensuring consistency checks remain intact despite concurrent modifications occurring independently yet concurrently. Common pitfalls and how to avoid them. Newcomers frequently encounter difficulties when first learning dynamic programming techniques. Misidentifying suitable candidates for DP solutions remains one of the most persistent challenges beginners face. Incorrectly formulating recurrence relations leads directly to flawed algorithms incapable of producing accurate outputs even after correct implementation attempts. Careful validation procedures help detect such issues early during testing phases. Bugs arising from improper initialization routines commonly plague novice codebases. Ensuring all boundary conditions receive adequate treatment prevents cascading failures later down the line. Debugging dynamic programming programs demands specialized tools capable of visualizing intermediate results alongside final outcomes to trace back exactly where discrepancies originated initially. Resources for deepening your understanding. Several authoritative texts serve as excellent starting points for mastering dynamic programming fundamentals thoroughly. Classic references include textbooks authored by renowned figures who have made substantial contributions to field advancements over decades. Online platforms offering interactive coding environments facilitate hands-on experimentation with real-world examples, reinforcing conceptual knowledge gained through reading alone. Engaging actively with sample problems enhances retention rates considerably. Communities dedicated specifically towards discussing dynamic programming topics thrive online today, providing rich sources of insight derived from collective experiences shared among peers worldwide. Supplemental materials covering mathematical foundations strengthen analytical abilities required for tackling increasingly difficult problems encountered along professional growth trajectories within software engineering disciplines. Conclusion: dynamic programming presents itself as indispensable toolset empowering programmers to tackle otherwise formidable computational challenges efficiently. Its ability to decompose complicated problems into simpler components enables elegant solutions unattainable through alternative methodologies. By embracing dynamic programming paradigms proactively, developers gain competitive advantage, enabling them to deliver robust software products meeting demanding performance expectations consistently regardless of input sizes involved. HTML